Hello everyone, this is Vasant, a nine-pointer at IIT Bombay from the Department of Civil Engineering. In this video, we are going to solve a numerical on stresses on inclined sections. So this is problem 2 on stresses on inclined sections. This is the problem you can see here. So here a plastic bar is compressed in a testing device by force P is equals to 190 newtons using these two bars and one spring. Okay, and by applying 190 newton force they are trying to compress this plastic bar. Okay, so here also given that the spring stiffness is 1 by 6 of the axial stiffness of the plastic bar. So see, what is axial stiffness of the plastic bar? See, we already know that del is equals to P into L divided by AE, right? So P is equals to AE divided by L into del. So if you compare it with Fs is equals to K into X, then you can see over here K will be equals to AE by L, right? It is similar to AE by L. So this is axial stiffness. Okay. So axial stiffness, let us say it is K dash. So then K dash is equals to 6 times K of spring. So now we need to find out sigma max and tau max in the plastic bar. Okay. Means first we need to find out the P developed over here. Let us go ahead. Let us draw the diagram. See, if you are nothing is given about these two bars, it means you are going to assume these two bars is as rigid. Okay, means no deformation in them. So you are trying to apply 190 Newton force here, then it will try to go down. So that will compress the spring, and similarly it will compress this bar, this plastic bar, but it won't able to compress this bar because it is rigid. So the deflected shape will be something like this, right? So this will be compression in spring, that is del S. This will be compression in the rod, that will be del P. Del P. Okay. So let us redraw the diagram. So this is the rod. It's going like this, right? And 190 Newton over here. And spring, see, it is compressing, so spring will apply upward force on the this bar, on this bar. So it will be upwards spring wala force, that will be is equals to K into del S, and upward force similarly from bar, plastic bar, that will be is equals to P. Okay, this is point, some point O. Here there will be reactive forces, actually some reactive forces. So if you apply moment, see, this will be del S, this will be del P. So if you apply moment at O, MO will be is equals to 0, that is equilibrium condition. So you will get 19 P into 100, because this distance is 100, this distance is 200, this distance is 300 given in the question. But P into 100 plus K del S into 300 is equals to 190 into 400, right? So 100, 100, 100 cancels. We get P plus K del S will be is equals to 190 into 4. From this similar triangles, from similar triangles, we will get del P divided by 100 is equals to del S divided by 300. So del S will be is equals to 3 del P. So what is del P? Del P will be 3 PL divided by AE, right? So this will be 3P by K dash, right? K dash is axial stiffness of the plastic bar. So this is one equation, this is another equation, right? So if you go and apply this equation in this, you will get P plus K into what is delta S, that is 3P divided by K dash, right? That is equals to 190 into 4. Okay. So we already know that k dash is equals to 6k. So p plus 1 minute. This is k into s. Sorry, this is 3k delta s, right? This is 3. So we get 9k p by 6k. So k cancels is equals to 190 into 4, right? We get this will be 3 by 2. So 5 by 2, 5p by 2. 5p by 2 is equals to 190 into 4, right? We get p will be is equals to 190 into 8 divided by 5 newtons. Okay, this is p. But what we need sigma max. So sigma max will be is equals to sigma. We already know that is equals to p by a. So that will be 190 into 8 divided by 5 into 5 by 4. Diameter is 32 whole square. That will give us 378 kilopascals. Okay, and this is compressive. So if we know sigma max, what is tau max in axial loading case? Tau max will be is equals to sigma max by 2, right? That will be is equals to 378 kilopascals divided by 2. What is that? That is 189 kilopascals, right? So with this, we completed this problem. In next lecture, we are going to solve another interesting problem on this topic. Until then, take care. Bye bye from 9pointer.